Solve the problem above. I will now tell you how you find the solution in an explanation. The Lewis structure of each of the species can be found by looking at the central atom, which in this case is carbon, and then creating the structure by finding the valence electrons of the elements in the molecule and putting them into properly bonded forms. Remember that hydrogen doesn't have hybridized orbitals, and carbon, having a stronger electron affinity, can be seen by looking at its placement on the periodic table or by finding the number of valence electrons. Because of these factors, the hydrogens will only bond with the carbons in these species, while carbons are able to bond with both hydrogens and other carbons. In hybridization, there are s orbitals, p orbitals, d orbitals, and f orbitals. Luckily, since carbon and hydrogen have relatively low valence electrons, you won't need to go farther than the p orbitals. In addition, the species in the problem have negative and positive signs, which indicate either gaining or losing an electron. The way to determine the hybridization when looking at a central atom, in this case carbon, is by simply counting the number of atoms that the designated atom bonds to. Or, if there are lone pairs, count them as if they were bonds to find the correct hybridization. Part A. In the case of H2CCH+, the organization of the bonding between atoms is already given with two hydrogens bonding with one carbon, which causes the hydrogens to lose their valence electrons and leave the carbon with two valence electrons. Then, that carbon will be able to form a double bond with the other carbon atom, which leaves the first with no more valence electrons and the other with only two. The second carbon will then bond with a single hydrogen, which leaves the carbon with a single valence electron. Normally this would make the molecule unbalanced, but because of the positive sign in the molecule, the last electron is taken from the carbon, making the equation stable. When hybridizing the species, the number of bonds for the first carbon is 3, with 2 being the hydrogens and another being the second carbon, though the double bond only counts as one bond. Therefore, the hybridization of the first carbon is sp2. The second carbon is bonded to the first carbon by a double bond and one hydrogen, making the hybridization sp. Solution B. In the second species, H2CCH3+, the structure of the first two hydrogens and carbon are arranged in the same way as in A, with the difference being that instead of a double bond between the first and second carbons, there is only a single bond. The other difference is that there are now 3 hydrogens that are bonded to the second carbon. By having the number of hydrogens bonded to the second carbon increase to 3, along with the single bond with the first carbon, there are no more valence electrons in the 3 hydrogens or the second carbon. In the case of the first carbon, which is only bonded to 2 hydrogens, and the second carbon by single bonds, which would normally leave a single unpaired electron, but, just like in A, there is a positive sign that takes the last unpaired electron away from the molecule, making it stable. In the hybridization, the first carbon is bonded to 3 atoms, with 2 being hydrogen and 1 being the second carbon, which makes the hybridization of the first carbon sp2. The hybridization of the second carbon is made up of 4 bonds, with 3 being hydrogens and the last being the second carbon, which makes the hybridization of the second carbon sp3. Solution continued. C. In the last species, H3CCH2-, the order shown is the reverse of B, along with replacing the positive sign with a negative. This does not mean that the actual configuration needs to be changed, though, so the carbon bonded to the 3 hydrogens will still be referred to as the second carbon for the sake of consistency. In this species, the bonds between the second carbon, first carbon, and the 3 hydrogens are the same, with all but the first carbon being free of valence electrons. The difference is that while in this species, the first carbon may still be bonded with two hydrogens. The negative sign in this species causes the single unpaired electron to become a lone pair by adding an electron to the carbon. The hybridization of the first carbon only has 3 bonds, with 2 being hydrogen and the last being the second carbon. However, the lone pair in the carbon can be moved to the p orbital and acts as another energy level that causes the hybridization to be sp3. In the hybridization of the second carbon, there are no lone pairs, so the number of bonds is unchanged from B, which makes the hybridization sp3.